I will introduce the advancements in the so-called work package 2 that is focused in the simulation, and in a particular simulation that is based on the hybrid twin concept that is being applied to the two processes that are involved in the project, the ATL and the FFF. This is a joint work with ESI group that is not present today in the meeting, Mustafa Megaed, and also with a lot of interactions with APC and with all the experts in the material domain, because in order to simulate, we need plenty of inputs, and this input concerns the materials and the processes. So I would like to start with introducing the concept of hybrid twin and the necessity of using this kind of hybrid paradigm in the modeling and the simulation of these processes. This is due to the fact that models are models, but here we are addressing very complex physics, and in general, models can offer, models based on physics, of course, can give some predictions that are not stupid, but in general are not perfect. On the other hand, we have data, and we could imagine that by taking the data, we could also construct models, but the problem in that case is we need a lot of data, and you know very well, all the people participating to this call, that in engineering, data is synonym of cost and complexity. So an approach that is based purely on data is not good, too expensive, too delicate, and a modeling that is only based on data in models based on physics is not good, because the physics is very complex and our models contains many simplifying hypotheses. So finally, the idea is to put both together in this concept of hybrid twin that finally consists in two twins, the virtual one on the left, that is the virtual prototype of the process, the model that is based on physics, and on the right, you have the digital twin that is an emulator of the reality that is based only on data. On the right, data and artificial intelligence. On the left, physics manipulated by standard simulation tools of applied mathematics. And the idea is to iterate between these two guys, the virtual and the digital, the physics and the data, in order to create this new paradigm that we call hybrid, in particular hybrid twin. So on the left, you have your virtual prototype that is based on the laws of physics, that you are trying to manipulate very fast by using model order reduction that we call smart virtual prototyping, and that we are introducing in a system level when there are many physics or many components that are dialogating. And this creates the virtual twin as a combination of these three ingredients: a virtual prototype that is given by the laws of physics, that we can solve very efficiently by using these model order reductions that we call physics in real time, and that we could introduce in the model of the process of the system in this system model. So this is the traditional simulation of the past. And on the right, you find the digital twin, in which now we replace the laws of physics by the real data. We replace the solution of these models by using discretization techniques that appears on the left, but something that is taking the data and create a model from the data by using machine learning. That is one of the technologies in artificial intelligence. And as soon as all this is ready, you have a model of your system and you have your digital twin. And the idea, obviously, is to connect these two guys, because the one on the left is not enough. We introduce many simplifications, and the physics is extremely rich and complex. And we are not only interested in making things on the right, because the data is the data, but there is not so much, it's not big in general in engineering, and trying to construct everything from the data, this is too expensive. So the idea is when we combine both, the physics is giving us the first level, and the data is there in order to enrich the physics. So now the digital twin is more to enrich the things that we know than to replace all the things that we know. And this is the concept of hybrid twin that we are trying to introduce in the project in order to model the ATL and the FFF. Today, in the presentation today, I'm focusing on the left because the physics is there, the data is coming. And until now, we are working more in the things that we know in the laws of physics, that in the data that is coming very, very soon in order to start the digital part and at the end of the project, combine both in order to create this hybrid twin. So our three protagonists are the data, the ATL process, and the FFF process. And I would like to start speaking a little bit about the data. The data is the material. And in the material, there are many data that we need in order to feed our make diagnosis, prognosis, and decision making. The first one is, obviously, we are speaking about complex material. We need the viscosity and the thermodependency of this viscosity. This is something that is standard. So it's not, there is no risk. This is only something that we can obtain very, very easily by using a rheometer. We need all the thermal properties because we are speaking about processes that involve heat transfer, but this is also quite standard. We need some geometrical properties, but this depends on the process and the system that we are addressing. This is quite easy also to have access. There is something that is very important and is very difficult, that is how to describe a surface. Why? Because we have tapes, we have composite, prepregs, and now the surface is not perfectly smooth. You have something that is a rugged surface, and you have surface in the place in which you would like to ensure the consolidation. This means the diffusion of the molecules. And molecules can diffuse only if the contact is perfect. And diffusion of molecules cannot occur as soon as there is an air gap at the level of the surfaces that are in contact, because surfaces are not perfectly planar. The surfaces are rugged surfaces. And we need to describe all this. And for that, we are using first a profilometer in order to extract the data. We receive many, many sheets. And in all these many sheets, we are extracting the topography, the surface, by using this profilometer at different positions in each one of the sheets that we receive at the top and the bottom surfaces. And for each one of these surfaces of each one of the sheets, we are using 17, we are making 17 measurements in order to obtain in different locations to have something that has the repeatability, and in order to isolate the profiles along the fiber direction, in the perpendicular direction to the fibers, and probably in other orientations. So for each sheet in the top and the bottom, we are making measurements at 17 positions in a small part in order to extract from them the profiles in the direction of the fibers and in the perpendicular direction. And this is something that today is already done, and we are making the analysis of the data. So it's coming very, very soon, but now all the measurements have been performed, and now all the profiles are obtained, and we are using one technology that we call TDA for topological data analysis. That is a very nice technology, very robust, in order to extract the descriptors that are richer than standard statistical descriptors for rugged surfaces. How it proceeds? It takes a rugged surface, and at each local minimum and local maximum that are neighbors, like the red, green, and blue square, we isolate the mean and the max. And we have different couples, min max, min max, min max. As soon as this has been identified, and this is very easy, as soon as you have the profiles with a computer script, you can represent this in the so-called persistence diagram that appears on the right, in which you have the mean on the horizontal axis and you have the max in the vertical axis, and you can see that you have the 7, 9, that you have the 9, 10, and that you have the 11, 14, that are the three blue dots that are associated to the different pairs on the image on the left. As soon as we have the persistence diagram, we can move to something that is called the lifetime diagram, in which, more than speaking about birth and death, min and max, we are speaking about min and the lifetime. The lifetime is the difference between the max and the min. That is the distance of the blue dots on the left to the diagonal of the square. And you have the 7, 2, the 9, 1, and the 11, 3, that are exactly the 3 points on the left and the distances to the diagonal. As soon as you have this, as in mathematics, we don't like dots, because dots has not a dimension, is something that is a Dirac delta that has an infinite value. In order to proceed mathematically, we prefer something that is smooth, and for that, to each one of these points, we are assuming a Gaussian distribution, and at each point in this square, we are making the addition of the contribution of each one of the Gaussian distributions. And the important thing for you is, at the end of the day, we arrive to this kind of image that appears on the right, the so-called persistent image, with a very good news. All the surfaces that are similar has the same persistent image, even if the profiles are very different if you try to superpose one to the other. Obviously, you can imagine that if you have a surface and you take two profiles, even from the same surface, point to point, they don't coincide. There are never two profiles that are exactly superposable, but obviously, from a topological point of view, the persistent image is the same. And this means that at the end of the day, I can classify the different surfaces depending on these images. And this is one of the cases that we obtain in 2 dimensions when you are using the TDA, the 2D TDA, related to one of the surfaces coming from Dominio. What is the use that we would like to make of all this? We would like to use all this in the simulation of ATL, because this root surface contribute to the consolidation. What is the procedure that we are following? First, we have a real surface. We can obtain the topological image, that is this image on the bottom on the right, with the blue, the pink, and the yellow. And from the other side, we have the right surface that I can represent by using, for example, wavelets, that is the image on the top. So this is the characterization of the surface. The real one on the left, the wavelet representation of the real surface on the top, a topological description of the surface on the bottom. So this is surface and its 2 descriptions. The real one based on a wavelet description, and on the bottom something that is more statistical. And as soon as this is ready, this means we can start to simulate the ATL by applying a laser. You are applying a heat flux, and you are trying to move with a certain velocity. There are many properties, as you can see on the right, the conductivity, the velocity, the angle in which you are applying the heat, and we just add 2 new parameters. This image is the first time that you can see it, because now the important thing is you have the temperature of the substrate, that is important, but you have also something that is very important, H in the substrate. That this means the thermal resistance between the tape and the substrate. Why we are introducing this thermal resistance? Because this thermal resistance is increasing as soon as the contact is not perfect. And when sometimes we are applying the tape on the FFF filaments, the contact is not perfect everywhere. And in order to take into account that we are applying the tape in something that is also a rock surface and the contact is not perfect, this means that there are two parameters that describe the substrate, its temperature that appears in the second parameter, and the thermal resistance that, for example, is infinite. This means that the heat cannot move to the substrate. So depending on the quality of the substrate and depending on the contact between the tape and the substrate, we can adjust this parameter H that is controlling the thermal heating. And here you have the parametric solution running. You can change the angle of the source. You can change the temperature of the substrate, the laser power, the conductivity of the different plies that has obviously in the range a minimum influence. You can change the velocity, that is a major element. You can change the thermal resistance, or you can change the number of layers. There are only 3, there are 6, there are 7. You can change the number of them. So this is almost ready, and it takes into account all the standard process parameters and the reality that is the contact between, or the rock surface between the tape that we are laying and the previous one that I introduced in the laminate. As soon as this is ready, we can simulate the consolidation, we can evaluate the evolution of the degree of intimate contact, and depending on the process parameters, I can evaluate the evolution of this intimate contact. And now by using machine learning, the idea is to correlate these microstructures, in particular the persistent images are the different points that appears in the classification on the right. We are using a machine learning classifier that we call code2vect, but it's a classifier, a standard one, in which each one of the points represent one surface, and the color represents the degree of intimate contact. And this is in the offline step. This is in the training. Now online, as soon as there is a new surface that is coming, we create the persistent image. We can evaluate in which position is in the database. And if it's very close of the yellow one, this means that the thermal resistance is very high and there is a big risk that the process is not good. So this is in order to control the process. Now, if we are moving to the FFF, at this moment, there is only a numerical study. The different data is coming very, very soon. But you can see here the first simulations about the filament that we put on the substrate, how it is deforming due to the viscosity, due to the weight. And now, obviously, this was a first tentative in order to model the evolution of the shape of the cross-section. In particular, it will depend on the deposition temperature and in many other properties like the temperature of the substrate, the viscosity, etc., etc. So as soon as this is ready, now we are trying to put all the ingredients together, and with the help of IPC, the Innovation Plasturgy Composites Lab, and ESI, they are trying to make different. We start the simulation, in that case, of the filament injection by using different gaps between the nozzle and the substrate and different scan speeds. And obviously, for given properties, viscosity, etc., we could obviously to have the first simulations that should be refined, obviously, but this is the first simulations about the deposition process. Obviously, we can change the gap between the nozzle and the substrate to 0.3. And in that case, obviously, because this planar surface, the filament that is being layered has a very planar or sheet shape. Making the first verifications, and this is something that is going on. And the idea at the end, and this is only a preliminary result, is to compute the final geometry of the filament, depending on many parameters, as just mentioned, the gap between the nozzle and the substrate, probably also the temperature at which the deposition is made, the temperature of the substrate, many parameters that we need to determine. But in this case, I will showing you at the last slide a parametric solution in which the shape of the filament depends on 3 parameters, one that controls the viscosity or the thermal dependence of the viscosity, another 2 parameters that control the heat exchange between the filament and the air and the filament and the substrate. And as soon as this parametric solution is ready, you can see here in the video that by changing the first parameter, you have in real time the change of the shape. By changing the second one is coming, you can also evaluate the change in the shape. And by changing the third one, you could again to evaluate the impact, the sensibility on the shape. So the idea is to continue this work. At this time is purely numerical, but the idea is finally, depending on the different parameters of the process, of the FFF process, trying to create a parametric solution like the one that I introduced before, this one that concerns the ATL, creating something similar, a kind of parametric solution in order to evaluate the evolution of the shape depending on the process or material parameters. And to finish, I will show a short video in which there is something new with respect to the past. Now, we have in the core of the filament, we have a rigid fiber, that is the case in Dominio, and around there is a polymer that can deform. Obviously, we assume that the filament in the core is quite rigid and finally is not deforming. And now you have the evolution of the temperature field and the deformation, and the deformation of the filament. But in that case, you can see that the half of having something that is rigid inside is affecting a lot the deformation of the filament. Now the next step is, after our previous discussions, we are changing this filament that now is not more circular, is something that is irregular and that is placed with a certain eccentricity and that it has a certain orientation. So we are enriching the description of the filament, that the fiber that appears in the core of the extruded filament, in order to evaluate the impact of it with respect to the final dimensions and shape of the cross-section of the filament. And this is all. Until now, this first year is almost based on the physics, but now the experimental work is moving on, and we start to introduce and to assimilate the data. The first one is the one that concerns the surfaces that now has been evaluated, and we are trying to make the analysis based on the TDA and many other properties that are coming, or measurements that are coming very soon. And as soon as they arrive, this could serve to create the part on the right of the hybrid twin in order to enrich the models, that even if the colors are very nice, it's not sure that the solution is very accurate with respect to the reality, because the reality is much more complex than the modeling that we perform. And I think this is all from my side. Thank you very much.